the whole world at our feet, watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand open arms, this is home where we are, ever strong in the world that we made. I
Good evening, everyone. Let's see if this works. If I can hear myself on YouTube, I guess we can get going. And I guess, yes, I can hear myself. Perfect. So, hello everyone and Happy New Year. I know it's pretty late in January, but, well, Happy New Year nonetheless. Today's live stream is going to be... Oh, I'm going to move the mic out of the way a little. Okay, today's... Sorry, I believe I have a different setting on my microphone. I'm going to fix it. Okay. And okay, let's see if this works better. Let me know. I'm actually have the setting from the previous live stream. Anyway. Okay, should be fine. We're going to talk about the whole drama that hit everyone, I guess, who uses a computer just when the New Year's Eve was over, and then some articles starting to appear about with like theories that something might be going on behind the scenes, and then, well, you know, Intel published an article that like, hey, it's not only our CPUs, it's also probably others, and then everything escalated from that. So yes, we're going to talk about Spectre and Meltdown, however you pronounce it. I guess I'm going to give you some... It's going to be like this. I'm going to give you a lot of links. I'm going to tell you the basics about, well, I guess the theory behind what you need to understand about the CPU and how it works to understand the vulnerabilities. And then I'm going to implement well, kinda Spectre attack variant 1. Let's see how well that goes, but without actually breaching the security context of the kernel, and just focusing on the well, on the bug itself. It's also easier to do it in the same security context, but I'll explain how can it be done on, like, by breaching the context anyway. So today's moderator is going to be KrzaQ. KrzaQ, thank you for being here. If you folks have any question for me, then just ping this fellow. His name's here. And he will pass the questions to me as soon as I guess, open our secret channel. I totally forgot about it, yes. Still leave the first stream on the new year. Okay, done. Should be fine now. Also, thank you to Foxtrot Charlie for some help with some stuff related to the streams. Cool. I guess I have one more announcement. This book just came out. Well, it came out actually, I don't know, a couple of weeks ago, but I just received it. It's Attacking Network Protocols, A Hacker's Guide to Capture, Analysis and Exploitation by James Forshaw. James Forshaw is a really known security researcher working at Project Zero. And I didn't read the book yet, but I know James and he's like amazing, so I expect to learn a trick or five from that book. You can get it, I guess, on No Starch Press's website. So, okay, let's switch to the desktop view and let's get going. You don't have to note the links. I'm going to pass you the links on the channels on both IRC and YouTube channel, YouTube chat, but I will also post the links under the video in the description later after the stream, so don't worry about it. Well, first, I guess, does this even work? Oh, my zooming doesn't work. I actually did a full update of Windows. Let's hope it's a full update and not a fail update. And let's hope that the zoom it just didn't start, but it still works. Oh, it works, perfect. Yes. So, well, KrzaQ's site, if you are interested about C++, then check it out. Now, what you should be doing today is you shouldn't be on the stream, actually. You should be watching Jan's video, his lecture on Spectre and Meltdown, because he actually gave a talk a few days ago, a week ago maybe, at Real World Crypto Conference in Zurich, here in Zurich on the ETH, I believe. So yeah, this is the first link. It's short and it's technical and it's to the point. Totally check it out. Yeah, seriously, you should be watching that video instead of this live stream. So I will totally not mind if you just go and watch it. Jan is one of the people who found the bugs. It was quite interesting actually, because a couple of parties separately, independently of each other, found the Spectre / Meltdown / variant 1, 2, 3, whatever you want to call it. There were also some other names in circulation. So yeah, a couple of groups of researchers actually contacted Intel, AMD, and ARM about it. And yeah, and then when it became public, everyone either issued blog posts or papers or gave talks about it. So this is one of it. Now, everything, I guess, all the drama began with, I believe, one of these posts on Python's Witness on Tumblr. I'm going to also give you this link. It's basically an article about, like, somebody noticed mysterious patches of Linux operating system, like some page table thing, which was done pretty quickly, and they figured that, hey, something is going on here. Like, you normally don't rush this kind of patches really deep into the architecture of an operating system and not provide any documentation about it and so on. So they did some guesswork basically, and looking at articles on LWN, on like what was announced on the CCC conference, which happened in late December, and yeah, also some other evidence and so on. So yeah, and they came to the conclusion that well, invest in popcorn 2014 is going to be fun. They were totally correct, and yeah, but it's probably some kind of a bug in hardware. And yeah, that was quite close. Then Intel, again, well, there was some speculation that it hits Intel really hard, and then Intel said that, yeah, but we are not the only ones affected, and basically the embargo just crashed. And I think Jan from Project Zero published this blog post, which is really technical, really deep into the topic, so you might want to read it. Actually, it's really good. It also links to the papers, I believe, and also it's quite important to note that Jan is one of the people who discovered it. I'm probably going to mention him just because he sits like down the corridor. But there are also other people from who discovered this. It's Daniel, Mortis, Yuval, Paul, another Daniel, Michael, another Michael, Stefan, Thomas, Werner, and yeah, I guess I will be mentioning another person soon. So quite a lot of people discovered it, and yeah, it happens, especially that there's actually quite... Some people are wondering, like, what happened? Why did suddenly all these different parties discover the same vulnerability? So I think it was first reported in June last year to Intel. And well, half a year is a long time, so research collision happens. But in this case, it's not really surprising in my opinion, because if you watch it, basically followed the research that was published last year, 2 years ago, it was obvious that several parties were looking at how, for example, caching works and how other CPU low-level features work and how to use it to bypass ASLR. So yeah, it was obvious that if there's something like this, then multiple parties will find it, and that's what happened. So I don't find it weird in any way nor surprising. Yes, moving forward, yeah, I guess patches were all around because apart from, you know, Linux, Windows, OS X being affected, also, for example, Zen was affected. All the hypervisors were affected, actually. That's also true for BSDs, like FreeBSD, OpenBSDs, and I don't think they're under the embargo. So yeah, there's some, well, perhaps the disclosure process could have been done better to also include them. I don't know what happened actually, and yeah, I wasn't part of it. Then, yeah, Intel basically, well, there was a lot of speculation on, is this going to affect performance? How much is it going to affect performance? And I think Intel released a table. I should also give you a link to this. Here you go, where Intel benchmarked basically some, well, of their newer processors, because, well, it's from Coffee Lake up to Skylake. So yeah, I believe I have even older processors than Skylake. Well, for example, this machine is from which I'm streaming from, I think it's Broadwell. Anyway, and well, sometimes it seems that even you gain some power, like 106% of performance, but in other cases it goes down to, for example, 86% of performance. Everything depends on the benchmark and what exactly are you doing. So I guess the way the patches, the software patches which were implemented, they are kind of workarounds. They make the context switching between the kernel and the software more painful, as in latency, which means that the calculations should be fine. Everything like calculation related should be fine. On the other hand, if you're relying on issuing a lot of syscalls, then it might be worse. But in all honesty, I didn't look too deep into the performance. I mean, there is not much we can do about it. So yeah. So speaking about the about this bug, there's a really interesting blog post from July of 2017. So that was a year ago, from Anders Fogg, who is also mentioned in the papers. Basically, he tried to do exactly what Meltdown did. And I'll get to the details of what's Spectre, what's Meltdown in a second. Yeah, but for some reason it didn't work out for him, so he failed, and he put some notes on the blog post. That being said, yeah, if you read this post, this is like Meltdown. So he was like super close to discovering it. So here you go. Then, yeah, I guess there's another blog post on his blog about back collisions. So I'm going to also give you this. And there were some also funny stuff. Like, for example, I was somewhat like hysterically laughing when I saw this. Microsoft says no more Windows security updates unless antiviruses set a registry key. So I think this was following one of the patches where it turns out that antiviruses were doing some hooking, which they tend to do, and instead of using, you know, the official APIs they should use, and it basically crashed the crashed the update, or crashed the Windows after update. And this isn't the first time this happens. At least one of my bugs, which Microsoft was patching, the patch had to be recalled due to exactly this kind of issues. But like some weird antivirus, some were just yeah, did something that the patched version didn't like. Anyway, so yeah, it seems that also the antivirus vendors had to be taken into account when patching. Okay, Microsoft also had I guess I should give you a link to this. Microsoft also had done some benchmarks. Everyone was doing benchmarks, so that's a really hot topic. I'm saying yes because I guess it quieted down a little. The volume of this information settled down. Even like there was this topic on Slashdot that even NVIDIA GPUs weren't immune to Spectre security flaws, which isn't true, and this was later there was another article stating that no, but that's not the case. Actually, NVIDIA did some patches, but it was only in the software side and in the drivers, since drivers needed to be patched, but the hardware is fine. Yeah, well, articles were all around. I guess I'm going to link a couple of more. So here you have Hackaday, which is one of my favorite news sites, by the way. Then CrowdStrike. I think Alex Ionescu also posted on Twitter some screenshots with some exploits working really early on. This is, I guess, also a post from... Oh, what happened there? Yeah, this is also a post from him. You probably should know, if you're into Windows research, you know who Alex Ionescu is. He's like, yeah, one of at some point one of the co-authors of the Windows internals book, and co-authors, I guess, of ReactOS and so on. So really amazing researcher. Yeah, also Google had, you know, so Amazon and Google and some other providers like Microsoft were put on the spot because, well, this affects virtualization and like the VMs you are selling to your customers. So is it going to slow the performance? And Google quite quickly replied with another post. I'm going to also give you it if you're curious. How was it fixed? It was fixed with a red line. In all honesty, I didn't look what's red line. I don't know how it's implemented, so I cannot answer any questions about it. Computer file, however you say it, also has a video on it. Then there's another thing. I think Pancake on Twitter actually posted this link. And yeah, like compiler teams doing the fixes. So here you go, another link on the chat. All the links will be under the video. And I guess I'm going to give you one or two more links and we get to the technical part. First, like everyone was writing about it. Yes, and this is something I will be talking about a little more, so I'm going to leave this open. I am going to give you a link to the discussion on how to properly patch the Linux kernel, and also, I guess, to this blog post about Meltdown. Yes. That's all of my links, thankfully. There's one question from Kelly. What do I think about Linus saying that software patches for Meltdown Spectre are garbage? I don't know, I'm not a Linux kernel developer, so it's hard for me to speculate on that. I guess speculate is when you joke, because, well, all these bugs are about, you know, speculative execution. Anyway, yeah, I know he has a really hard stance on some things, so yeah, perhaps there's something in it. And I guess, you know, the software patches here are workarounds. This has to be fixed in the hardware, and if any performance is lost now, you will have to basically replace your CPUs and so on at some point to get a faster version which has taken these issues into account and done something about it. It's fixable in hardware, but it's not an easy process, and I don't expect, you know, the proper CPUs to be on the market next year or this year even. Why does Intel not patch their code that works in their processor? So you're referring to the microcode. I think they did. I think it caused some troubles. And I don't think everything can be patched like that, because the microcode handles only part of the things, but other things are like in silicon. So it's like not an FPGA, right? You cannot just reprogram everything. You can reprogram some of the things with microcode, and everything else is in hardware, and like some features around it might be in hardware. So, but they did release some patches, and there were some problems with it. Cool. So, too many links. Am I going to be banned on my own channels for spamming with links? I apologize. Yeah, it's basically when I was... So this topic was requested by a lot of people, and I started making a list of links to read before the stream, so I know something about it. I wasn't involved in this, so this is basically was a learning experience for me. Yeah, so a lot of links were collected and a lot of them were lost. Okay, so I'm going to start with theory behind how it works and what's the problem. So before we get to what's the problem, let's chat about how CPUs work and how they work and how they really work. So starting with how they work, you probably know that you just, well, the CPU executes machine code. So you might have some machine code like push rax, then move rax ebx, and then like, I don't know, ret or whatever. This will fail unless ret, well, maybe rax has some address, whatever, or abx actually has some address. Yeah, whatever, doesn't matter. So what you are learning if you are learning assembly or reverse engineering is you're learning that the CPU is going to first execute this instruction, and then when the instruction is over, then it's going to execute this instruction, and when the instruction is over, it's going to execute yet the next instruction. No, I was right, it was REX, never mind. This is how everything began years ago, basically. And there are a couple of problems here. Maybe not with this example, but the problems is that some instructions take a long time to execute and some are really fast. For example, if I would like to, I don't know, just change a flag in the registry or zero a registry, that's probably a really fast operation because the registry is in the CPU and the dice, like interacting with it is really fast. That being said, if you go to other stuff like multiplication, this is slow. If you go into division, that's even slower. And so there is math operations which are slow, but on the other hand, you have also memory access. The early computers, I guess, had, you know, there was like RAM, which was static RAM, so SRAM. And static RAM is quite fast. It's fast. It's really fast. And it's faster than DRAM, which we are using now, but it's also way complicated to, like, it takes more space on the silicon, so you cannot pack it so dense as you can do with SRAM. That being said, it's faster. But when we moved from SRAM to dynamic RAM, SRAM being, I don't know, I think it's called just flip-flops in electronics. My apologies, my electronic knowledge isn't so great. We moved to DRAM, where, especially if you studied Rowhammer, you know that DRAM is basically a set of capacitors. So you have a capacitor and you charge it to set a bit, and you discharge it to to remove a bit. Now, to read the state of a capacitor, you basically just like grab a little energy from it. I'm totally sorry for that being incorrect, but that's like physically, but that's what how you can think about it. It also ends up reading from a capacitor, you end up leaking some of its energy. And because you're leaking the energy from the capacitor, you're discharging it. Basically, then you have to, charge it again. And you have to do this I guess every 60 milliseconds or even more frequently. Therefore, well, that's not too great, and also reading the state of DRAM is also not too fast, so stuff slowed down. So yeah, I guess it's sufficient to say that RAM was slow and is slow now as well, regardless of if it says like 3 gigahertz on your dice, RAM dice. You still, if you read the specifications, you see that if you count the lookup time and so on, it actually takes like 19 cycles to actually grab the data from the dice, right? That's not the CPU cycles, but that's the motherboard cycles, if you will, or chipset cycles, however you want to call it. So yeah, so we have instructions which are slow, and what can you do to make it faster? Cool. So first the question, why do we use XOR register instead of moving 0? It's a historical thing, as in older CPUs that was faster. Currently it doesn't make a difference, but in older CPUs, and I mean like 25 years ago or 20 years ago, that was faster. And now we just do it because we've done it in the past. I don't think there's a reason to do it. If you discharge DRAM from zeros, where do all the zeros go? Is the dust on your CPU or your RAM dice, probably. Same with shifting the registers. Jokes aside, returning to how you can speed stuff up. So let's assume we have the following code, and this code is going to use memory. So let's assume that we have to put in a RAX register some, I don't know, something from the A register, because why not? And then you add, you for example put in RBX register 23, and then you add RBX to RBX, which is basically multiply RBX by 2, and then at the same time you, well, doesn't matter. In the end you, for example, add or XOR RBX with RAX. Yeah. So if you look at it from how to make it faster perspective, you basically know that this instruction might be slow. And to give you numbers, these numbers are more or less accurate, but do measurements if you need precise numbers. If the content of this memory, which is being requested here, is in the CPU cache, so if we have the CPU, you might know that the CPU has cache, quite a lot of it nowadays. I think my CPUs have like 16 megabytes of cache. Cache is super fast and super expensive. And by super expensive, I mean it's not that much super expensive, but yeah. Anyway, so yeah, and there's L1 cache, and basically each CPU core has its own L1 cache. There's actually the L1 data cache and L1 code cache, and accessing a register on the CPU is basically instant. Sorry, and accessing L1 cache is like, let's say, I don't know, like 6 cycles, maybe 4 cycles. Let's assume 4 cycles. So a CPU has, for example, 3 billion cycles per second, right? Now you have, if it's not there, not in that L1 cache, then maybe it is an L2 cache. And L2 cache, it takes a little longer to access it, let's say 10 cycles. And again, these numbers are just to give you an example, they are not precise numbers. Maybe it's an L3 cache if it wasn't an L2 cache. And yeah, then it's like, let's say 15 cycles. And no, it's not in any cache, then, well, we need to grab it from RAM. And this DRAM here is when we move from like 15 to, this 15 might be a little larger, it depends, but never mind. We move to like the 100 to 200 cycles territory. And this is assuming that there doesn't have to be any page translation done in the process, or it has to be done, but everything needed is in another cache for page translations. I'm not going to go into that. Long story short, if everything goes wrong, fetching data from RAM can take up to 10,000 cycles. So this instruction, even though it doesn't look too scary, can be potentially either fast or super slow. So the CPU is going to basically stall on it, and so some smart person said, then how about we execute the next instruction if it doesn't depend on the result of the previous instruction, which is a good thing to do. So this instruction can be executed before the above instruction will be executed, will finish executing, and by finishing executing, I mean it's called retiring. And retiring is actually applying the results of execution to the context, the registers, and so on. That being said, we cannot retire this instruction yet, so we cannot, actually put 23 in RBX, because maybe this will do a segfault. If this does a segfault, then we cannot retire this instruction, but we can try to speculatively execute it. And the next instruction, when we're done with this one, we can execute also the next instruction and do the addition. And then here, when we get to this instruction, we actually have this ready, but we have to wait for the result of this instruction. So for the move from memory to finish. So the CPU would stale here probably as well. And when we get this, actually correctly get no six segs and everything worked, then this will be retired, and then this instruction, the already calculated result, which is somewhere in the buffer ready to be retired, is going to be retired, then this is going to be retired, and this is going to be calculated. So thanks to this, these two instructions didn't have to be processed after this instruction, they could be processed ahead of the time. So this is one of the things which has been done to actually improve the latency. KrzaQ also says that XORs emits shorter instructions. That is true. I think using also sub instead of XOR to 0 register emits the same size of an instruction. It also depends what register are you looking at. But yeah, in general you are correct. So yeah, this is what's going on in modern CPUs, and there are also other mechanisms. The second important mechanism which I should tell you about is branch prediction. And branch prediction, let's do it again. So this, and this time we will actually have some, let's say, the same move, because why not? So this time we get 32 bits. Then we compare AAX to 1, 2, 3, 4, because why not? And then we, depending on the result, let's say if it's not equal. If it's not equal, then we actually go away. Otherwise, we do we do some math, right? So let's say we add to AAX, we add ABX, and then we jump somewhere again. And in case of go away, so let's assume that go away is here, go away, we do yet again something different. For example, let's say we XOR AX with AX to actually clear the register. Now, again, we know that this might stall or might not, doesn't matter. The question is here, when we get to this instruction, to the jump, well, we basically get 2 branches, right? So the CPU can either execute this instruction next, or it could execute this instruction next, and we basically need to decide which branch is it. And we will know which branch is it for sure as soon as AAX is fetched and this instruction is retired. Then we will basically know, right, where to go. But again, this instruction might take a long time, so the CPU tries to make a guess. Like, oh, I think we're going to go actually this direction. Like, it's not going to be equal, so we should speculatively execute this instruction and wait with its retirement, obviously, until until we know that this branch will actually be taken. And if this branch will not be taken by some chance, well, just ignore the results that we have in the buffer and go the slow path of actually executing the next instruction in the normal phase. I guess some CPUs either had implemented this, or there was at least some talk of going so speculative execution going actually both branches, and just committing the results of the proper branch after we already know that the branch has been taken. I guess I just there is just a question appeared about it. So I'm not sure how on Intel it's done, but it can be done. So going back to this example, the CPU tries to it's quite complicated, and it's explained in Jan's blog post, for example, on Project Zero site. But the CPU tries to remember where did the execution go last time. If, for example, the execution almost always, like 30 times already went this branch, then probably there is a high chance that it will go again this branch. Obviously, this is just a prediction, right? It might fail, but perhaps if it already went 30 times there, the next time it will also go there. So it tries to remember basically a hash, not the full address of this jump, but a hash of this address. So there's like some h of, I'm going to just write PTR as the pointer here, and put it in a hash table of predicted branches, and put the destination address. This is the destination address, obviously. So thanks to this, when the CPU has to make a choice here which branch to speculatively execute while waiting for this instruction to slowly fetch the data from the RAM, it can look into this branch prediction hash array, hash table, however it is implemented, and if there is a guess that it will probably go this way, it can speculatively execute the next instruction. Yeah, and this is quite important. This mechanism is really important because in the past, every jump basically meant that you had to clear the instruction cache. It would just be cleared because, well, the CPU had no idea what branch is going to be taken. And now the cache can be pre-populated with the possible next branch which might be taken. And this saves some, you know, grabbing code from memory in this example. Now, yeah, that's, by the way, why so-called loop unrolling was popular back in the days. Loop unrolling is if you have a loop and, you know, for example, for 1 up to 1000 do something. Instead, you do the something, for example, 10 times and increment the iterations by 10, being careful about the tail, obviously, because thanks to that, the jump, which is included at the end of a for, jump to the beginning of a for, would not flush the cache. And yeah, and now we don't have such problems because we have branch prediction. So this is the second thing which is quite important to actually understand about the CPUs, to understand Spectres and Meltdown. And yeah, so speculative execution and branch prediction. And with that, we can, I guess, go to the variants. So the supervisor asks, could you use glibc unlikely for that? And if not, what is it there for? So before branch prediction, or maybe even when branch prediction was a thing, but before that, you could hint the CPU that a branch might be taken or not taken. And on assembly level, it was just prefixes to jump instructions, like, you know, like the ret prefix for rep prefix, for example, or I think even that prefix was used to tell the CPU that, hey, probably this jump will be taken, or hey, probably this jump will not be taken. And this in higher level languages, you could also use that. But to use it, as the best supervisor writes here, sorry, here is actually, where is it? Here, yeah. My screen is inverted, sorry. glibc unlikely to signal that. It might be still useful today. I'm not sure how much it gives since, well, the CPUs have no branch prediction algorithms which learn by themselves. Okay. So let's talk about the bugs. There are 3 variants. 2 of them are called Spectre, and the third one is called Meltdown. So the first variant works like this, and this is the variant which I will implement later on. Okay, so we have 2 contexts. Yeah, we have the user space. So this is the user space, and this is the kernel space. Or like ring 3 on this side and ring 0 on this side. And in kernel, you need a specific code pattern. Now, you either need to find that specific code pattern or use a JIT. For example, Jan used the eBPF JIT, which is present in Linux kernel for this, to create the pattern. So you need a pattern, and the pattern looks more or less like this, and I'm going to write this in high-level language. This is, assume it's like some kind of function, and you control the part of, well, you control some input. If index, you control the index, is less than size, then do something, and this looks really funny. There is some buffer, like I'm going to call it mem, and then there is another buffer, let's call it R, and R is actually where you'll be leaking data from, and here goes your index, and then this is multiplied by some size. I'm going to write 512. It has to be basically like a large cache line-ish size. Anything from 128 to 1000 might work. It depends on the CPU. For me, 128 worked best. In the exploits I looked at, 512 were used. Basically something like this. So what's going here is, I guess, quite easy. You control an index, and if the index is in the size, this size is related to this array here. So this is a proper check. There is no buffer overflow here because there is a check that checks the boundary of the array. Then we'll put the index here and grab the byte. Let's assume it's byte. It should be a byte. Let's grab the byte from this array and then multiply the byte value by 512. Why is it important? I'm going to explain later, but long story short, what you want to do is you want to hit a line that a different value of a byte would hit a different cache line in the CPU. And this is important for detection. Now in the user mode, you basically do something funny. You somehow control the memory, as in you can do time measurement. How long does it take to access this memory? And by determining this, how long does it take to access a memory, you basically determine whether the memory area was in cache or was it not in cache. If it was in cache, then access to this memory area will be fast. Like I said, like 5, 10, 15, 50 cycles. If it wasn't, if it was in RAM and it had to be fetched, then access to this memory is going to be slow, and you will be able, thanks to this timing, to actually say if it's that it has that it wasn't in memory and it had to be fetched. Now you call this function through the contexts 30 times, and these numbers which I'm giving you here are not even experimental. You basically have to figure them out yourself. But 30 times you call this to train the CPU's branch prediction that this condition is always met, and therefore this instruction is executed. You trained the branch prediction, calling it 30 times with the index, for example, index being equal, you set the index to 1. Because let's assume that 1 is less than the size. And the size can be small. It should be small, probably. Like the size should be around 16. 16 worked the best for my case. And then when the 31st execution comes, you execute it once with index set to a rather crazy value, pointing to some out-of-bounds memory which you want to leak. For example, 55. 55 is totally more than 16, therefore it's out of bound. This check will obviously fail. However, the next thing you do is you actually make sure that the size here is evicted from cache. It is not in the cache, so it has to be fetched from RAM. Therefore, fetching this value and evaluating this expression will be slow. Will take 200 cycles, and in that time the CPU can engage into speculative execution based on the branch prediction, so it can speculate on executing this. Obviously this will be in the end not taken and the results will be discarded. However, what you also make sure is you basically make sure that this mem area, which is quite a large area, is not in cache, and there are ways to do it. Because if it's not in cache, that means that when the speculative execution starts executing, it will have to, it will fetch this value from the array, the value from index 55, because, well, it doesn't know about boundaries or anything. It will just fetch the value and assume the value is in cache. So this value here, this needs to be in cache. And then it's going to multiply it by cache page, as I'm going to call it today, I guess. Maybe that isn't the best description. And it's going to try to fetch the value from that address. However, this isn't in memory, so the speculative execution will also stale here, but it will tell the cache engine, the cache prefetch engine, hey, this memory is probably going to be needed, so fetch it to cache. And then, well, this never executes because the memory, this condition is finally checked, and yeah, this never executes. And because this is proper anti-buffer overflow check. So it returns, and what you do next, you actually start going through this mem area, through this memory area, and checking how fast is it to access, for example, this byte. Oh, it's 200 cycles, it had to be fetched from RAM. Okay, then perhaps this one. Oh, it's actually 15 cycles, it was in cache. Now, this whole memory area was not in cache, so what happened? Why is it in cache suddenly? Well, because on this address, this index, starting from this pointer, there was a byte, let's say 17 hexadecimal. And therefore, the speculative execution engine told the cache engine to prefetch this area of memory because it might be needed. Therefore, we know that since it, due to this multiplication and due to differences in like this being actually split into multiple cache lines, that if this exact spot was preloaded, well, the byte in this array in the memory we normally don't have access to had to be 17. And this is the variant 1. It basically allows us to leak kernel memory or like memory from a different context using this kind of neat trick of basically having a really large memory area and seeing what gets loaded into cache by the speculative execution engine by measuring cache timings. Now, I know there are 3 questions, so I'll get to them in a second. What I want to mention is I wanted to mention this thing. This is a paper from 91, as in almost 30 years ago. This paper discusses that the cache, the CPU cache, can be used as a side channel, which means they already knew back then in 91 that you can measure the cache, the access to a memory area latency to know if something was in the cache or wasn't in the cache. This is, of course, like a super long way before branch prediction and speculative execution began appearing in CPUs, I guess, at least in the desktop CPUs we use. But it's like the first most important part of a puzzle. So yeah, this thing is going, I guess, way back. Yeah, I'm going to give you the link to it as well. There are also I also found some other papers. I actually have a whole stack of papers like that I read preparing. Also, if you have this POC or GTFO, it's not the last one, but the previous one, the one before that. There's actually this one here. Yeah, the 1404 is like flash plus reload side channel. That's also about like measuring cache timing, so you might want to check it out. Okay, let's get to the questions, and then we'll get to the second variant and the third one and start implementing it quickly, or at least look at an exploit. It's not working? Why is it not working? It works for me. If the link doesn't work, I'm going to put it in the description anyway. So, HonoraryBot says it isn't likely about basic block ordering, it's like profile-based optimization in MSVC. Really, is it? I didn't know that actually. So HonoraryBot might be actually right, but likely in glibc might be more about the ordering of blocks, so that the block which is more probable is next to the code which is evaluating the expression, therefore they're like in the same cache line, for example, and can get executed really fast. It might be true. I didn't know that side of it, so thank you for chiming in. Then we get something from KrzaQ, who I guess... Oh, he actually sent a link to explain how it works. So I'm going to give you it here. Again, if you have any questions, then ping this guy on the chat, because he puts the questions in a super secret medium that we're using. Their best advisor says, so this was the first time an AI was tricked to gain control over a system. It's a good question. I'm not sure about the first time, because, you know, neural networks are used for face detection and recognition, so like unlocking an iPhone with a printed out face might have been the first one, but yeah. And but it's not, I guess, a neural network. It's more like a least recently used, or like most frequently used kind of thing. Is this related to TLB? TLB is the cache I mentioned that contains the page table translation address, like something like a side buffer, I don't remember. Anyway, no, it's not. It's not related to it, because it actually is about the cache lines and not the page accesses, though there might be a variant of that as well. Okay, so the question was, what is 512? 512 is about, it's the size of a cache line. Not the page size, because the page in you know, virtual memories, usually we think about it as 4 kilobytes. Obviously larger pages can exist, but 4 kilobytes. So no, this is about the cache line, because the cache is also split into chunks, and the chunks, I think the like L1 cache line is like 16 bytes or 64 bytes. I actually lost count in the modern CPUs. Okay, let's quickly go through variant 2 and 3, and I'm going to then go to the coding part. So variant 2 is actually something a little different. In the end, it boils down to variant 1. It basically is a way of tricking the CPU into falling into variant 1. Now, the way you do it is quite funny. When we talked about branch prediction, I've mentioned that the hash of the source address, like if you have a branch, right, it has a source and it has a destination. And not the full address, but the hash of this address is actually stored, so it's the hash of the address. Now, the hash isn't as large as the address is. That means there will be collisions. And this is actually trying to abuse, like variant 2 is trying to abuse the fact that if there is like some kernel code here, and it has a jump here at this location, and it normally jumps here, you can make, in the user land, you can make your code placed in a specific location, which is totally different, has a totally different address than this one, but their hashes match. So this is like some kernel address, but yeah, these hashes are actually identical. It's also more complicated, because there are like 3 different branch prediction algorithms. Check Jan's lecture or his blog post or the Spectre white papers. But it boils down to this. And then you basically teach the kernel in your process that, oh, this branch, it always goes here to this code. And this code happens to be the JIT I mentioned. Like this is the part which does which I showed on the previous example, that basically does the array reference, then multiplication, then another array reference. And you train it, so you do this a lot of times, and then you trigger execution of this address. This might be like part of a syscall, for example, right? And the kernel goes here, then it goes like almost here, and then there is some RAM fetch, which is super slow, so the CPU starts to, well, obviously continues speculative execution and looks for this hash in the prediction table, and it actually gets what we have taught it. And we taught it that, oh, it always should jump here. So the CPU starts to speculatively execute this code. But that doesn't make any sense. For example, this branch would never ever jump here. It's not possible, for example. It might be an indirect call which never would jump there. But, well, it is the address which was in the branch prediction tables, so this is what the speculative executioner start to do, and it falls down into, again, leaking the data, leaking the bits, the bytes, using the same way, especially that you might control some registers. Obviously, this will not be committed anywhere, the result of this, so this isn't really executed, it's only speculatively executed, and the only thing you can see of this are the side effects being the cache timings changing. So this is the second variant, and now the third variant called Meltdown is well, what the person I referred to previously described in their blog posts. That means it's a little easier. And I guess it's the most spectacular one because it's the easiest to exploit. And it's like this. Let's assume that we have the following code. 2 racks, or actually, I don't know, 2 AL, whatever. We move a byte from RSA, and then we, what do we do now? And then we do move to RBX, so yeah, let's do it like this, via RBX RAX times, how much can I multiply it here? Only 8. Well, whatever. I'm going to write in high-level code now, because it's a little easier and it doesn't matter. I'm going to multiply it by 512 again. This is again the cache line sizes. It can be smaller, for example, 128. But let's assume that this is the size of a cache, one cache line. And then, well, we basically do the reference, so we do like some x is equal to racks. Yeah, we do the reference. Now, here's the trick. No, my code. Once again, RCA. Okay, then we do the multiplication, and we do the reference. So x equals racks. This is the same. Yeah. You know what I mean. Okay, now. The important part is you put something which is super slow, like again fetching from RAM here, so that speculative execution is actually time to execute. So this is like fetching from RAM, and this is speculatively executed. Now RSI is actually in kernel memory. This is executed in user content, but this is in kernel memory, somewhere not accessible memory. What will happen when this will start executing? Well, obviously, there will be a zigzag, right? So there is going to be a segmentation fault. And but since this is speculatively executed, it turns out that on Intel CPUs, it will actually fetch the data fine. Especially if this data is in cache. It should be in cache, so it's faster than whatever is going on here. So it fetches the data from the kernel fine, and it then multiplies whatever byte was by code to select. It basically selects a cache line, and then here it tells the prefetching engine of the cache, hey, please fetch this cache line, and then we do again the time measurement on the cache buffer, right? So this is the wherever racks here is pointing. So I don't know, let's call it P. This is P, and we again check that, hey, perhaps this was in cache, and thanks to this we know that it's byte free. So yeah, this is Meltdown. Basically, speculative execution engine in Intel CPUs doesn't do ring checking or page write access checking when doing speculative execution on some CPUs, and this could be used to leak data. Yeah, so even if the seg fault, arises here, you can just handle it and like in a handler just jump after this code, so this code never actually does get really executed. So you get here, and yeah, and then you check the timings, and you get you've leaked the data. So that's pretty fun. Okay, so let's do questions and do the coding. So why there are no separate caches for every ring? And this is actually a good question. Another good question is, why doesn't the speculative engine actually check the writes? I think the access writes are in the cache lines, next to the cache lines. They are fetched together. That was mentioned, I think, in one of the papers. So it should be, or the blog posts. So yeah, it should happen. But yeah, it doesn't. I guess will have to be some changes around this in the CPUs. I think AMD wasn't actually, like, Meltdown doesn't affect AMD, but these other ones do. But please refer to well, official announcements from Intel, AMD, and ARM about which CPUs are actually vulnerable to which version of which variant of these vulnerabilities. I'm sorry if I mixed something up, but I think I got it right. Does this mean that any CPU with branch prediction is vulnerable? What makes RISC 5 immune? Is this the RISC V or is this the RISC 5? Anyway, immune to Spectrum attack. Do you think that very long instruction words would also be affected? All good questions. I guess it boils down to checking. I didn't check, so I have no information, but if there is branch prediction and there's some separate context, security context, you might want to check. It might be vulnerable. Who knows? About the second part of the question, yes, I don't see why not. Unless they don't do any... you'd also need speculative execution, by the way. If you don't have speculative execution, then none of this works. And I actually don't know if Itanium, which you mentioned, or the RISC-V CPUs do have speculative execution. I don't know. Yeah, I guess we are going to... so this is my expectations for the next half of the year. We're going to see more patterns emerge, which can be used to leak data. And there are also going to be patterns found in the kernel, and we're going to know about different CPU families, which actually have, you know, speculative execution and branch predictions. Speculative execution is actually, like, pretty top-notch, so I'm not sure, like, too many families actually have this implemented. What about fixes? In all honesty, I focus on the exploitation side, so I don't know too much about how the fixes work. One of the ideas is to just remove all the to remove basically all the pages related to kernel memory from the page table when the CPU is executing the user mode code. And normally the pages are very just not accessible, and there's a big difference between being there and not accessible, as we saw in Meltdown, and not being there at all. There's being no mapping to be able to access that data. So this is one of the patches which were introduced. There's also RedPoline, which I don't know how it works, so or is it related even to what I said. So yeah, I guess I cannot answer that question. Sorry. Yeah. But I'm pretty sure there's like a lot of information on the web about it. Why the microcode update is needed? Ah, that's an excellent question. I don't know exactly the details. Nobody knows exactly the details because Intel is not releasing any details about how the microcode works and what is in the updates. Yeah. I guess they can patch something about this inside the microcode. Yeah, but nobody knows what you can patch exactly, right? There is some reverse engineering done on the AMDs, but not on Intel's. Honorary Bot says the problem in the Meltdown is actually a race condition between speculative execution and validating access rights in the PT. Yeah, might be true. I mean, if it's a race condition and not that there is no check, but there is like only a check which isn't fast enough, it's... thank you for correcting me technically. That being said, the outcome is still the same. though it might explain like why it didn't work for in the initial approaches to it. So thank you for chiming in. Aren't there any folding mechanism to undone what was executed in the speculatively executed branch? Yes, nothing of that is committed to the register state, RAM, or whatever. It's not committed until the instruction can be retired. That being said, RAM fetches are not undone. RAM is fetched or prefetched. So yeah, this is the side effect which you can actually measure. Yeah, and Honorable says that's why the cache is filled. Yep. Get behind reverse engineering the microcode ASAP. So the problem here is that it's encrypted, and I don't believe Intel's microcode encryption has been broken yet. AMD's isn't encrypted, and I think that's why it's somewhat analyzed. I think it's signed though. What about return address stack prediction? Is it exploitable in the same way? There was some talk about it, but I don't think it was used. But oh yes, I think it was mentioned in the in variant 2 as one of the branch prediction algorithms. But I don't know if any exploit is using it, but it was mentioned. So yeah, the how is it called? Like the shadow call stack can be used. Maybe can be used, because you know it all boils down to the details. How is it exactly implemented? Okay, KrzaQ repeats that I should start decrypting the microcode in that case. Yes. Now let's find my terminal and we can do at least some basic coding. What do I do here? Here we go. This is, what am I looking at? I'm looking at part of my old code, but I'm going to start a new code. I'm going to do this. I'm actually going to code in Vim in the command line, because this isn't my machine, it's as in my streaming machine, because I kind of feared that the video compression that's going on and processing in the background is going to make stuff unpredictable. So I'm actually SSHing to one of my servers. Which I know it doesn't have too much load, so we can experiment with it. Okay, so that's one thing. The other thing I need, I'm actually going to have a cheat sheet somewhere on the screen displayed, just because it's like this. I stayed up until 3 AM trying to figure out what was wrong, and then I spent a couple of more hours in the morning, and it turned out that order of my variables was wrong. So it gets tricky to get everything correct if you're writing the code in a high-level language, and I'm going to write this in C. And yeah, so yeah, Spectre 1, this is what it's going to be the topic. Okay. Actually, I'm going to minimize this a little, because first of all, you don't see the end of the screen, and second of all, I don't see, oh sorry, this corner of the stream, because I have this microphone, which you probably heard more than so. I'm sorry for scaring anyone if that happened. How old CPUs are affected? I mean, the oldest that are affected, I actually don't know. I mean, we would have to look back at when was both branch prediction and speculative execution introduced. I don't know. Probably Intel or someone else checked. So if someone would check it and would know, then just yeah, shoot KrzaQ a message. Some standard libraries and also one non-standard library, and that one is going to be x86 in Trin, which we need for measuring time and also flashing the cache. Measuring time is going to be done in cycles using read timestamp, which basically gets you the number of cycles from the reboot of the machine. And yeah, so that's that. Let me maybe... So I'm going to basically do this in steps, and the first step is going to be having a buffer. I want to check which part of the buffer was actually accessed. So I'm going to have a volatile buffer, and I'm going to also define something called cache page. I don't like this term, but everyone's using it, so okay. And I know that for this machine 128 is the better size than 512 used by in almost all exploits you can find on the web. You can find a lot of. What's the target operating system for this exploits? That's an Ubuntu not updated LTS. One of not the latest one, but before that. We can do let's do this, and 1604, so that's actually an old Ubuntu, and uname-a, yeah, so it's a pretty old kernel, I guess. Should be perfect for this exercise. Okay, so yeah, I'm going to call this like the detector buffer. So yeah, and doesn't matter too much, but I want it to be of bytes. So the cache page, and I'm going to make it the size of 256 cache pages, whatever that means. Okay, now what I need is I need to create a function which we will give that function. I'm going to basically go the safe route about it. So we're going to give this function an index and ask it, hey, was it in cache or was it in RAM? And by index I actually mean a cache index, no, sorry, a cache page index, not a byte index. And I'm going to call it, I don't know, time maybe, and it will return, let's say, like N32. I didn't, at first it will return just the time difference. Time, like bench check. Sounds good. And as I said, it's supposed to take the index. Okay, now how to time it correctly. And I'm going to actually need another function. This function is going to, well, two more functions. First is going to be called the sync. I'm going to compile this without any optimization. Compiling this code which I'm writing with optimizations will remove half of it and it will not work. So it's important, no optimizations. It's that kind of a code. It's hackish. No, don't use it on production, basically. And event 32, I guess, x. And x is absolutely not used here. Yeah, I'm going to do this. And okay, so that's one thing. And the other function I need to write is basically, if you've been programming on Atari or like other 8-bit computers, you're going to remember this function is going to be called delay. And it's going to basically be a busy loop, which does nothing. So for volatile int I equals 0, I less than 1000, I++. It's just going to count from 0 to 1000 and commit it to cache. Why is this function useful? Because it gives time for example, the prefetching cache prefetching engine to actually grab data from memory, and we are going to use such delays somewhere. We should not use sleep, because sleep is a call into the kernel and it will freeze our process, and we don't want that. We want to basically do all the measurements and everything in one go, between, you know, getting rescheduled by the scheduler. Yeah, so such busy loops were used for delaying stuff back in the days. Okay, so again, what do we do first? First, I'll have to make sure that the detector is not in cache, and to do this, I basically have to go through each cache line. So for int I equals 0 up to 556. Yeah, yeah. Okay, fine. There's this instruction called mmcl flash. It's actually an intrinsic, I believe it's called, for did I have a browser? I had a browser. For a cl flash instruction. Cl flash is flash cache line instruction from x86. It's a normal Intel instruction. I think It cannot be blocked. Anyway, what it does, it basically you give it an address, and that address is evicted from all the levels of cache. If yeah, and it also, you know, stores all the data which was in the cache in RAM if any is needed. So I'm going to grab the detector, and I already know that I'm going to have to do a cast to void because it's actually a volatile, and this function requires a non-volatile argument, and it will complain. Plus we select which which cache page do we want to clear. So we clear this one, and it will clear everything in the detector. Now we basically have to wait while the clear is being done, so we delay here. I don't think it's instantaneous. At least in my test, putting a delay here was important. A lot of this stuff which I'm doing, I'm going to say that, oh, I tested it and it's good to put it here, or this value I like, it works best on my PC for some reason. It might not be the case for your PC. It might be different for your PC if you're going to test it, and you might have to like try different values, try different settings, different setups. For example, here you might want to go with a fence, for example. A fence didn't work for me, but you might want to try it. A fence basically makes sure that all the memory operations have been ordered here, which I thought that ordering should be fine here, but it's not enough, and delay is better in the end. Okay, and now we basically just access the memory, so we do create two variables for timing. We grab the rdtsc. Did I do... I'm going to quickly check one thing. Okay, no. Yeah. So, oh, it's actually like two unders. rdtsc. If you don't know what it does, it actually returns a 64-bit value, which is again the number of cycles from the reboot of your machine. This is the most precise timer you can have on a CPU. That being said, it's not precise up to the cycle, I think. There's some mess, but I might be wrong. I know it changed. And in between this, I'm going to actually access the memory by calling the sync function and accessing the memory of the detector. On a given index, I have to calculate the index still, so... oh, wait. Sorry, the index I already have here, I just have to multiply it by the cache page. Yeah, okay. This also makes sure that actually the index is in cache, so it doesn't slow me down. And yeah, and this will be either fast or slow, and what I'm going to do is I'm going to just return the time difference for now, then I'm going to change it. And yeah, let's see what happens. Let's do something like this. Let's do print for, you usually do it for several iterations, so I'm going to do it for 10 iterations. Do you see the code at the bottom of the screen? Yes, you do. Perfect. I'm going to scroll it a little. No, 10 is not too much. I'm going to actually make a function which does this. So since when measuring time, you usually like to repeat the experiment a lot of times to, you know, get for example the average, which is better than grabbing one value and then figuring out that due to some reasons the CPU actually prefetched like some random pages. So you want to do this yeah, a couple of times. So I'm going to create, I guess, a uint32 like called sum. It's going to be equal to 0, and I'm going to add everything, and I'm going to return the average. The average should be fine here. It's better than the minimum or maximum, at least in my opinion. Let's try like 1000 times. Okay, 1000. It should be fast anyway. So sum, and we add to the sum the check on the specified index, and then we return the sum. Let's do another define here somewhere. Let's call it count, like, or repeats, maybe, whatever. Count is fine. I think others also called it count. Count 1000. Okay. Okay, and now I'm going to basically go through all this let's just go through like from 41 hexadecimal to, because in the end letters will be interesting to us, to Z. So you know, these are like basically, if you're new to C or C++, this is OX41 or 65, and this is whatever, like 56 or whatever is the decimal Z ASCII character code. So you can treat it as numbers. And for each one, I'm going to print the time. So I'm going to, I guess, do this. And the time being an integer for check2, and the index. Currently, it should, like, everything should be not like evicted from cache, because everything is in RAM. I didn't touch any of the detector's pages. Everything should be the same-ish values. Okay, and let's see if this actually works. So yeah, 0. Index is undeclared on 52 because it should be I. Perfect. This is fine. I don't know why it's complaining. Oh, I know, because it's not fine. I actually missed one argument. My apologies. Okay, and I'm going to run it. And yeah, these values are rather small, and these values actually, like, this is probably the fastest fetch from cache plus execution time of instructions plus storing of RDTSC result, which can happen. So it's not working correctly, which is, I guess, expected. So well, what else do I need to do here to actually make sure that this is evicted from my cache? I can increase the delay. I can increase it by, for example, putting another 0 here. Let's see now. Yeah, the rest of the coding is going to go this way. Like, I'm going to change random things and see what happens. Okay, not good. I think this delay is just too small. So I'm going to, I guess, put some... let me see how I did it in the past. Okay, I did it in a funny way. So let's change this delay a little, and I'm going to make the CPU do some stuff here. I guess since I'm going to do some stuff, I don't need this. I've also seen others do it in a similar fashion, so I'm going to... This is just random stuff. Like, it doesn't matter what's here, it matters that it takes some time to do it. Okay, let's see now. Still everything is in cache, which I don't like. Maybe my... maybe something else is wrong. Okay, I'm flashing the detector. And then here I'm checking the count of index. This is what I also do here. Oh, I know. I might here have to actually put a load fence, otherwise... yeah, otherwise it might do... Yeah, now it's fine. It's actually like... the instruction would be reordered, so the time would be fetched faster before the load would be actually done. And this is fine. This is like how long it takes to fetch from RAM. This is in cycles, in CPU cycles. Again, my CPU doing, I don't know, like 3 billion cycles per second, so this is not a lot of time. To answer your questions, in JavaScript, no, not in JavaScript. Yes, this is doable by the way in JavaScript as well, which is quite scary, isn't it? Atari XE XL, I had XL800, which was cool. XE was also pretty cool, though I didn't have it. How would you go about controlling the cache in a higher level language than C? Exactly the same way. I guess you wouldn't have CL flash instruction, but that's fine because you can just use the cache for something else, like create a huge array and then start randomly poking at the array for a long time, and that makes pretty sure that it evicts everything else from the cache. So you can still use such side effects of operating on high-level code to interact with the cache. And then, you know, if you fetch something in a high-level language from your array, then it will have to be put back in the cache. And how long it takes to fetch it, well, if you have high-precision timers and JavaScript has them, then you can measure it too. Okay, back to our code. So as we saw, the number of cycles are counted now in hundreds, right? So I'm going to hide this. Okay, therefore, I'm going to somewhere put, I guess I'm going to put here, here, yeah. I'm going to basically put accessing the detector at some place. For example, at place which I will call of letter G. I have to obviously multiply it by the cache page. Why does it... That's not helping. Okay, I'm just going to touch it, so I'm going to call it with a sync. Sync does nothing, but it should be fine. And then I'm going to delay again to make sure that it's fetched. I guess I could also make an else here, so let's do both. And let's see if the timings differ for letter G. And as you can see, they differ. Because of what I've just written, well, there was a fetch to cache done. So therefore, G letter, or the area actually, which I'm going to call G letter, is already in cache. However, none of the other areas are in cache. All the other areas are obviously in RAM. Yeah, therefore, these are pretty long. So this is how you measure accessing the cache. So this is only the first step. Now, the second step is going to be making the funny function, which are actually making some secret, which I need to leak. So, like this. And this is also, I'm going to call it like secret size. And secret size is going to be, I'm actually going to move this in a second. 16. 16 is the value which worked best for me. And this is the semi-secret array. It will actually like be somewhat longer than the size says. Apologies. However, this part will be normally accessible by my code, and this part will contain the secret which I will have to leak. And there will be no way in the code using proper execution models to reach this side afterwards. Because in testing I am going to reach it, but afterwards I'm going to deny it. There will be proper bound checking and only this part will be accessible ever. And using speculative execution and branch predictions, again, I will try to leak this part. So it's going to be the secret size, and I'm going to add some extra spacer, and I guess it's going to be char, because I know what char, car, whatever you want to call it. And I'm going to put 4. Yeah, so this is 16.0 because I actually don't care too much what's at the beginning. I prefer it to be zeros. It doesn't. It somewhat matters, but doesn't matter too much. And here I'm going to put secret. Yeah. If you're wondering what is this, this is how you concatenate constant strings in C. It only works for immediate strings, like immediate values. Sorry, how is it called in C terminology? It's like literal strings. I believe it's literal strings. So yeah. And I'm actually going to move it here, and then, sorry, I also have to move this. And then I'm going to create another variable, which is also volatile. Volatile means that the compiler will not optimize out reaching to the variable, even if it has already grabbed the value like a second ago. That's not all what it does, but that's how you can think about it if you're doing this kind of coding, which I am doing. Cool, so this is the size, I don't know, uint32 is fine, and secret size, and it's going to be equal to obviously secret size, yeah, which is fine. I need it to be evicted from cache, to be slow, so I will do that in a second. Now I need to write the function which actually is like guarded access to the secret. So let's do the return value doesn't matter too much. I'm not sure if I'm going to go for a return value. I'm probably going to just like do this. And let's call it guarded secret. And it will take an index again. And what it will do, it will check if the index is less than secret size, and if it is less, let's do this. Oh, actually, if it is less than, it will do. It doesn't matter if it's like something. It's just here for the compiler to keep it what I'm going to write now. It's going to do access the detector array but not under the certain index, but under the secret of index multiplied by cache size, cache page. So again, this normally shouldn't leak anything because, well, again, this array is split in half and the first half is accessible by everyone. Now you can imagine that this piece of code is actually like in some other security context. For the sake of this example, I'm not going to put it in another context, but you can imagine it is there. So yeah, again, this is just an example. So okay, now instead of calling this, I'm actually going to call guarded secret and with the index. And it should actually still work-ish the same way, but I'm going to, at the beginning too, I'm going to actually put a letter like G here, so we can do the testing, right? I'm going to later remove it, but for now, just to be sure that it still works. And obviously it doesn't work because why would it? Let's see what I did break. So secret, let's see, maybe this isn't needed. Well, why is there a load fence? It should be, well, whatever. Okay. Oh, because the index probably, I've changed how the index works now, so the index should be, yeah, let's leave this load fence here, whatever. The index works now in a different way, so what the index now does is basically, yeah, I can do this still, but I should set the index to 0, because index now is the number of byte I want to leak, and not really this. So let's do it like this. I'm going to create another function called get byte, because why not? And it's actually going to be uint8. And it's going to take the index of the byte, and I guess I'm going to move this. Oh wow, this is not what was supposed to happen. Okay. The best supervisor asks, what is the fancy IntelliSense for Vim you got there? It's just the basic config I'm using. I don't know why it chose to actually work like intended, but yeah, it's on my GitHub if you're interested. But it's just the basic Vim. There are no plugins installed on this machine. Okay, getting back here. So this is fine because we use this for index. This index isn't actually the index anymore. There are going to be two things here. First is going to be the index of which byte we want to leak from the secret, and the second thing is actually which letter we want to check, because we will be checking only one letter at a time. You don't have to do it, you can optimize it, but it's safer this way, and you know, live stream and stuff, I want it to be safe. So okay, so that's index, and there's like byte to check, like, or value to check, maybe value to check. And this value to check, index is going to be used here, but the value to check is going to be used here. Or actually, it's going to be used here, value to check, and value to check, perfect. Now, here I pass it the value to check, which the value to check is downstairs, so value to check, okay. And here I actually give the index of which byte do I want to leak. I want to leak the 0th byte, and now the value to check goes, sorry, the index goes here, no, wait, index goes here, and here goes I as the byte I want to check. And now I need to get the byte, I'm not going to print it yet, I'm going to print it later, from 0. So let's see if it works. Yeah, it works. As you can see, for G, again, the timing is better because, well, we here told it to access the secret, and the secret at this index is G. Therefore, G multiplied by cache size hits the part of the cache after which we checked. It was like the only part of the cache which was not in RAM, but was actually in cache. So thanks to this detector, we actually know that it was a G there. But again, this is normal execution. This isn't speculative execution. There is no branch prediction yet. Now we can start playing with a branch prediction. I'm going to remove this G and change it with 0 again. I will do some testing later on in a different way. And I'm going to start to want to actually fetch the 16th byte. So 16th byte is out of bound, right? It's more, 16 is more than what I have here. The secret size, therefore what is here, this variable is not changed in any way. Therefore, if I have it here, it will never allow me to leak any byte this way. So we start going into what Spectre is really about now. First of all, we need to do a funny thing. We need to train the branch prediction to actually always go to that branch. And to do this, I guess I'll need another define. I'm going to call it train. Like, how many times do I want to train it? Let's say 100. And also another thing is like, I'm going to call it frequency. That's not the correct name, technically speaking. It's like, how frequent do I want to, because that tag is going to be like this. I will work on the branch predictor, but then from time to time I'm actually going to try to access out of bound quickly. 1 time in 10, for example. And this is the frequency. How frequent do I want to do that out of bound access? 10 times every 10 time. Every 10 time I want to do it. Cool. Now, so I need to do like, I need to train the branch prediction up to 100 times. The detector is already flashed, cleared. Then, okay, and this is where it starts to be funny. First of all, and this is, I guess, more important for speculative execution, but I guess I can code it here. I need to remove from cache the, well, you know, the secret size. So that I need to remove it so that that's not what I wanted to show you, sorry. Where is my function? Oh, it's here. So that this evaluation is super slow, and the speculative execution which I count on to actually execute this has time to execute. So this needs to be slow, therefore this needs to be evicted from cache and needs to be somewhere in RAM, somewhere far in RAM, and has to take 200 cycles to fetch. Therefore, going back here, we remove it. Then we do stuff, delay. We delay, so it's actually evicted. And here is going to be quite funny. I'm going to write something which I'm going to then comment out. What I want to do is freak is 0. So if this is the time where I want to actually jump out of bound, I do the guarded secret index. However, all the other times I just want to access index 0 or like some other index which is okay, and the branch prediction will actually always enter this area. So I can remove this now. Okay, and I guess, maybe I'll leave it. Now, this won't work because these are branches, and the branch predictors seem to actually look at a path instead of just one branch sometimes. So this will tip off the branch predictor, but hey, actually the path is different, so something might change. So I cannot have any ifs here, any different paths. I have to do everything linear. So this is where math comes in. So I'm going to create, I guess, another variable is going to call it TRX, being binormal index which I train, and it's going to be like just I with secret size. This is TRX is the correct inbound index. Okay, and now where the math kicks in. How do I? Okay, let's call it address. And this is actually something I copied from one of the exploits I found on, well, partly copied, like one line, because it didn't work for me and it started when I ended the line. Anyway, if I actually I modulo frequency -1, yeah. So what happens here is actually, if this is 0, then I'm going to get -1. -1 obviously is 0xFFFFF. So after doing this, I get 0xFF and like 4 Fs here and then zeros. For zeros. If this isn't -1, so this wasn't 0, it was 1, 2, 3, 4, 5, then this is actually going to be 0, and therefore after this is just going to be 0. So I have something like this. Now, what I want to have in address is I want to have either all zeros or all Fs, so all bits set. Therefore I can do, well, you know, basic, like, I probably should find, just to give you a link to that exploit, the Spectre 1 exploit. Exploit surprisingly is written with 1 I. Yeah, I think it was either this or both actually. So I'll give you a link if you want to see some proper code. I actually written, like, I've read the papers and I've written my exploit and it didn't work, so I started looking at others' exploits and I was like, my code is identical, like, why doesn't it work? And it turned out that, like, you actually need to properly have the sizes and other stuff, and after some messaging it worked. Anyway, so that's why I actually have some links to other exploits which I know work. Okay, so I do this. Now I have either all zeros or all Fs here, depending on whether it is time to go or it's not time to go. So now what I can do is I can, what did I do there? Oh, this is another funny thing which I'm basically going to select whether I'm going to use the training address, so TRX, or the index which I should be using. So it's this. No. I'm looking at my cheat sheet. TRX index. Okay. So what's going on here is actually quite funny, because it address is again either zeros, and if this is 0, then this whole part is 0, and 0 XORed with anything is just that anything. So it's either the training address, or in case this isn't 0 and this is all Fs, then this is taken into account, and therefore it's the training address XORed with index we want to leak. And when you XOR it again with the training address, you get training address XORed with training address, and two same things XORed each other, cancelled each other out, so this is just 0, and we are left with the index. So this is a nice trick to avoid having any ifs, but in the end it does basically this with TRX here. It's like the same code, it does the same things, but it works in a different way. Yeah. And now, having this, I can do the guarded secret address, and this is not going to tip off the branch predictor that any of these things will happen. I think if you look at the exploits I linked, it's explained better there. Cool. So it's trained, and yeah, we can run it, or we can try to run it. I'm pretty sure it's not going to compile. It actually runs. I'm not sure what is it counting, but we'll get to that in a second. Okay, it's pretty slow though, but that's fine. So, this is the point, I guess, where I start to fiddle with my variables. So I'm going to just set it to whatever I have set in my code, because trying to figure out it live might not work. This is fine, this is okay. It's fine when I do this. I'm not sure about this fence here. And when I do this, let's see if it got any better. Okay, what I'm looking at is okay. So what I'm doing now is I'm training, well, making slow fetching of the secret size when I'm in guarded secret. So this is one thing I'm doing. The second thing I'm doing is I'm selecting whether I want to do the attack, which is the index, or actually I use a training address. And then I actually call it with the address. I guess I can print the address to make sure that this is now how this language works. Too much Python. Yeah, I can do this, and I can do exit here, so I can actually check if I have correct values here. And let's see. 16 is the number where I actually jump out, which is fine. This is out of bounds, this is fine. And all the other iterations should have less than 16, and they do have less than 16, which is fine. It also, I guess, tips off the prefetch engine that I'm actually like walking byte by byte, so it might prefetch the next 16 bytes, which is beneficial for me because I want the next 16 bytes to be in memory already to be able to leak them. Cool. Now let's look at this function again. This function is fine. Now I'm going to check if my cache detection works again, because I might have failed at somewhere, and to do that I'm actually going to increase this size by 1. So that I actually, you know, that it's allowed. What I'm doing is allowed. So this is, I basically disabled my attack. I fell back to the old version just to check if the timings are better. And this is Ubuntu again, Ubuntu 16.04. Okay, and it works in this case. So I have, you can see that, you know, there's secret there, right? Like the character's secret. So S has the lower time, so it works okay for just the plain cache, checking the cache, but it's not the speculative execution yet, so I'm going to remove this. And let's go back to debugging. Okay, train. Fiddling with this, it doesn't really give me too much, because it actually is to fiddling with this is to improve the stability, and I don't have any stability yet. To increase this velocity a little, I'm going to do from I don't know, from H up to STU maybe. Let's check that out. These are like pretty strange, but you can ignore them. Okay, so S isn't detected, which is a bad thing. I do have correct indexes, because otherwise my previous check would not work. Then I'm going to do some variable reshuffling. I'm going to move this here, for example, and see what happens now. Nothing yet. The value here is a little lower than in other places, but it's not the kind of lower value I'm looking for. It might be an accident, basically. Okay, I'm going to use my cheat sheet to actually figure out how to... oh, I can make a lower count so it's faster. Though the count I think is still too slow. Now, I'm going to change a little the way it works here. Instead of adding up to the sum, because I'm using the average, I want to make a majority vote, basically. And I'm going to introduce two other variables, which will be called in RAM and in cache. And I will do a voting system whether this actually works. So to do it, I need, I guess the sum isn't really needed anymore. Okay, so TM, that's the time. Now, if the time is more than 80, 80 is the value which you would say the boundary lies between how something needs to be fetched from RAM and something was actually in cache. So if it's more than 80, then it's in RAM. Otherwise, it's in cache. Now, the question at the end is this actually in cache or is it in RAM? And I guess what I can return is, yeah, I can return if it was in cache as 1. So if in cache, there are more in cache votes than in RAM votes, then I'm going to return 1. Otherwise, yeah, I am going to return 0. Okay. And here, now I'm not going to display timings anymore. I'm going to display either 1s or 0s, because this might be a little better for me. I'm also going to, for the time being, display these, like the actual values for in cache and in RAM. So now I know how the voting works. Yeah, not too good. Okay, so this means it doesn't work. If it would be just not stable, then this would be, for example, 500, 500. That would mean I need to tweak a little some other things, but that's not it. So let's go back to the debugging. And it's going to be probably something really, really stupid. Let's play with the cache size, for example, cache page. No, nothing there. So I'm going to go back to my maybe secret size. I'm going to decrease the secret size, and I'm going to actually move this to a couple of lines so I can comment out this part. No, that's not it either. Maybe I should increase it to 24. Oh, one more thing. Here, get byte. This should be like secret size plus 0 for now. So I'm going to actually repeat the last experiment, because there was 16 and 16 doesn't make sense in that context. So yeah. Nope. So this is the moment where I'm actually going to go with my cheat sheet and see if I have everything somewhat working. Oh wait, I'm looking at the wrong cheat sheet. Oh no, that's the final one. Okay, so I can show it to you, I guess, why not? Now let's actually do it the other way around. Okay, let's see what I have done in the past and I have failed at doing now. 16 here, is this 4, 8, 16 and then the secret, that's fine. What's the order of variables? Because again, this might be important. This is... okay, and for some reason I have another variable here, which is like the detector size. I don't know why I use it, but that doesn't matter too much. And yes, this kind of stuff matters because of cache layout, cache lines and other stuff. So yeah, just like moving variables around might actually change something. So this is fine. This is now sorry, it seems that this is, you can see only part of the window. I'm going to fix it for you. Okay, my apologies. Thank you, KrzaQ. Now, this is quite similar. This doesn't matter. The delay is longer. Delay is fine. Actually, I'm pretty sure it's fine. Do stuff. Is this identical? It isn't fully identical. Looks pretty identical. Guess I'm going to change it, because why not? Nope. Okay. Then we go down. Okay, so in the check, I don't actually have this because this is on an outside function. Maybe that's my problem, but it shouldn't actually be. First, I remove this and I walk by the cache page, which is the same thing I do here. So this is fine. Then I actually don't delay over there because I do the delay here. So, okay, that's fine. Then I do this. Oh, and there I do it here. So, yeah, I guess I can. Maybe that changes something, I don't know. Let's just do it like this. Yeah, and it works. Seriously. As you can see, I have like 100% result that S was actually in the cache. And this now works with branch prediction, and it now works with speculative execution, because I still have, as you have seen, as you have seen, I still have this check properly in place. So now let's leak everything. So I'm going to do a couple of things. First of all, since this works with stable, I'm going to decrease the count to 100. Now I'm going to go back here to the whole alphabet. I'm not going to go through all the bytes. I'm just going to do the alphabet to save some time. And basically, what I need is let's just do this is going to be nasty, but let's do it. Zero is fine. If I'm going to comment this out, check to idx I is equal to 1, then ch is equal to I. Yeah, I'll let it keep going, and now I'm going to return ch here. No. Let's just put it in the loop. And put char. Okay. And I'm pretty sure I did something wrong, so I'm going to fix it here. Yeah, this is what I was looking for. So that's one thing. The other thing, here, I actually don't need it. Okay, and let's let it run for a second. Yeah, and leaked. So yeah, thank you Speculative Execution and Branch Prediction and Spectre variant 1 for actually working during the 2-hour live stream. And thank you to everyone for actually looking 1 hour how I debug the code. If there are any questions, there are some questions. Okay, so you still need to use volatile even that you use -0. I think 0 should be enough. But yeah, better safe than sorry, I guess. But maybe it would be enough. Yeah, I guess there you have it. So, unless there are any other questions, I'm going to, I guess, announce the. I'm going to upload this code, by the way, to GitHub. So if you want to check it out, but it's pretty similar to the exploit I linked for you. Some announcements. Next week is going to be a stream with Robert Święcki, or Jagger, who is the creator of Hongfast and NSJail, which is basically a lightweight sandbox using namespaces for Linux. And it's, I guess, if you played CTFs or created CTFs, you might be familiar with it, since it's like the tool of choice there. Thank you, Pavel, for the donation. Thank you very much. Yeah, I enjoyed it too. Anyway, so with Robert, we're going to discuss NSJail, his sandbox, and he's going to say how it works and so on. So it should be fun. It should be fun. And yeah, if you're into sandboxing or like defense mechanisms, you should enjoy the stream. He's basically one of the lead people at Google behind sandboxing as well. So that's that. The second announcement is, as you probably know, if you go to my blog, you should know, and this is my request to you actually. If you could go to my blog, the Ginvale's Game Dev Challenge for the winter, this isn't it actually, I thought that. Why is my blog so slow? I need to debug it. Yeah, never-ending story with this stuff. Okay, this one. The Ginvale's Winter Game Dev Challenge has ended, but the community choice award is still, the voting for it is still going on. So if you would have some time, there's actually a website where you can vote and you can test the game. So you can like choose a random game, click here to play, and you can play the game for a couple of seconds, and there are, I think, 12 games which are taking part in the competition. Just take a look and vote for them, whichever you like. The more votes, the better statistic we have for giving out the Community Choice Award. And the deadline for this is, for voting is, yeah, 28th of January, midnight. And then, I guess, a couple of days after that, I will announce the winners both for the Community Choice Award and for My Choice Awards. The games are pretty fun. The topic was, if you didn't look at it before, the topic was create a tactical turn-based game in JavaScript, and it has to be in one file, just one file, everything in one file, like the sounds, the graphics, the fonts, whatever, everything in one file. And it has to be under 20 kilobytes. So yeah, so take a look what people actually managed to squeeze in under 20 kilobytes in JavaScript. The games are best played on Chrome, on Windows 10, because that's actually the platform I'm going to use for testing. So that's the platform I used for, well, ask the people to test on. And I'll announce the winners probably after next stream. So thank you very much for today. Mara, thank you. And yeah, thank you, KrzaQ, for being here, and have a great evening. Happy hacking, and do read about Spectre, both Spectre variants and Meltdown, because that's actually pretty fun, and quite a good learning opportunity it was for me as well. So yeah, see you next week. Bye bye, and happy hacking. I'm going to leave you with some music, but unfortunately there is no mission today. Before we jump there, actually, there's the last week's mission. Oh, one important announcement. Murmus CTF is going to stream in a second. So, so yeah, basically go and check out his stream. And thank you again. See you. I'm leaving you with some music.
Summer in the hills, those hazy days I do remember. We were running still, had the whole world at our feet, watching seasons change. Our roads were